Welcome to CSC 201, lesson 4.3. We're going to start with the definition of a rational number. I've written in symbolic form. I will try to speak this in regular words. This says R is rational if and only if there exist integers such that R equals A over B, right? There exists A and B in the integers such that R equals A over B and B is not 0. So this just says R is rational means that you can write it as a ratio of two integers as long as the denominator is not 0. All right, so we're going to apply this definition to show that each of the following numbers is rational by writing it as the ratio of two integers. 32 over 5, 32 fifths, that's done. It's already written as the ratio of two integers. 7, we can write as the ratio of two integers by writing it as 7 over 1. 1.844, we can write as the ratio of two integers by doing 1,844 divided by 1,000. And then 2 fifths plus 1/9, we know that that's rational. We can know that it's rational by adding them together, right? So this is 18 45ths plus 5 45ths, getting a common denominator, which is 23 45ths, ratio of two integers. Okay, now a repeating decimal, I'm going to show you a little trick for how to write that as a ratio of two integers. So we can say let x be 0.242424 . Okay, that means that 100x would be 24.242424 . And then I'm going to subtract the same thing from both sides of that equation. The 100x equals 24.242424. That equation, I can subtract the same thing from both sides. On the left, I'm going to subtract x, and on the right, I'm going to subtract 0.242424 because those things are equal, right? X equals 0.24242424. So I'm going to subtract x on the left and 0.242424 on the right. And in fact, I'm subtracting the same thing from both sides of the equation because that's just two ways of writing the same thing. So I get 99x equals 24. And if 99x equals 24, I can just divide both sides by 99. And I get x equals 24 over 99. And now I've written it as a ratio of two integers. Number 3, if m and n are both integers and neither m nor n is 0, is m plus n rational? Well, m plus n is an integer, right? Because the sum of two integers is an integer. We've talked about that. M times n is an integer because the product of integers is always an integer. So I've satisfied the two important parts, right? I've written m plus n over mn is a ratio of integers. The top's an integer, the bottom's an integer. And then the second and crucial part of the definition is that the denominator cannot be 0. Now, is it possible that m times n is 0? No, because the only way a product can equal 0 is if one factor or the other factor is 0. But we know that neither m nor n is 0. So that is not, those do not equal 0, and that's called the zero product property. So yes, m plus n over mn is rational. Satisfies the definition because the top and the bottom are both integers, and the bottom is not 0. Okay, here's one that is going to feel a little silly that we have to write a formal proof for it, but we want to prove that every integer is a rational number. So, for example, 7 equals 7 over 1. That's how we know it's rational because you can always put an integer over 1. So we just want to write this sort of formally. There isn't a lot of scratch work to do. our well-written proof is going to start with suppose that A is an integer. And then I'll say since A equals A over 1, and we can just say by properties of real numbers, A is rational. Prove that the sum of any two rational numbers is rational. Okay, so if I add two rational numbers, so that means I'm adding like P over Q, that's a rational number, and R over S. And when I add them together, I would have to get a common denominator. So I would multiply this one by S over S, and this one by Q over Q, and I would get PS over SQ plus RQ over SQ. And then once you have the same denominator, you can add the numerators. PS plus RQ over SQ. And then PS plus RQ, that's an integer because it's just products and sums of integers. And SQ, that's an integer. Because it's just a product of two integers. And SQ, it has to be non-zero to satisfy the definition. So SQ, is it not zero? So I wrote P over Q and R over S as rational numbers, which means neither Q nor S could be zero, right? Which means that SQ could not be zero. Okay, so I think I've shown it. Now I just have to write it out very formally. So I'm going to start with suppose A and B are rational numbers. Then A equals P over Q and B equals R over S with P, Q, R, and S, all elements of the integers, and Q and S are both not zero. Okay, so if A and B are rational, then they can be written as a ratio of integers with the denominators not zero. Thus, A plus B equals P over Q plus R over S equals PS plus RQ over QS. Now we just need to add in a couple of small details so that we can draw the conclusion. So we know PS plus RQ is an integer because PS, R, and Q are all integers, and sums and products of integers are integers. For the same reason, we know QS is an integer. And we know QS is not zero by the zero product property. Right, because we know neither Q nor S is zero. We assumed that earlier in our proof. Neither Q nor S is zero, so Q times S can't be zero by the zero product property. So since we have an integer on top, an integer on the bottom that's not zero, A plus B is rational. Use the previous result, the one we just proved, to prove that the double of any rational number is rational. So to set up this proof, I would say let A be rational. And I would need to show that 2A, the double, is rational. And if I want to use the previous result, I could say, well, 2A is just A plus A, And I know that the sum of two rationals is rational. I just proved that. I know it's true now. So that's it. Let's just write it formally. Let A be a rational number. Since 2A equals A plus A, and the sum of two rationals is rational, 2A must be rational.